right, 61. All right, tangent of x equal to 0. What x value or what theta value or radian measure will allow tangent to be equal, will have a ratio of 0. Look back. Tangent is y over x, so 0 is going to be 0 over 1. That constitutes as 0. 0 over -1, that's also 0. So 0, pi, and 2 pi. Next up, tangent of 2x equals to 1. That 2x kind of makes things a little more complicated, but if we do inverse sine, we can now inverse sine of 1 is just another way of saying, asking sine of what theta value will allow sine equal to 1. So these mean the same thing. It just allows us to create an expression without an equal sign here. So when is sine equal to 1? Well, sine is equal to 1 at pi over 2. So we can replace this with pi over 2. And that will allow us to solve for x. Same idea, 63. Sine of x over 4 equals root 3 over 2. Let's do inverse sine to figure out sine of what theta value equals root 3 over 2. And then once we find those radian measures, then we can come back and figure out, solve for x. So again, inverse sine of root 3 over 2 is another way of saying or asking sine of what theta value is equal to root 3 over 2. So we know that this is going to be in that pi over 3 family. Positive sign will be first and second quadrant. So we can set x over 4 equal to each of these separately and solve for x. Now, 8 pi over 3 is more than 2 pi. We know 6 over 3 is 2, so 8 over 3 is definitely more than 2. So this is outside our interval. We're only looking for x values between 0 and 2 pi, so we're only going to keep 4 pi over 3. Okay, we're going to solve the following exponential equations, or equations involving natural log and exponential function base e. Remember a couple of the following that can be useful. Anything raised to the 0 power is 1, so e to the 0 is equal to 1. And then natural log of 1 is equal to 0. Okay, so if I want to solve for x here, e to the x plus 1 equals 2. I'm going to try to get e to the x by itself. So I'm going to subtract 1 from both sides. So e to the x equals 1. So one helpful thing to know is anytime I'm looking to solve for a variable that's sitting in the exponents, it's easier to get that variable by itself if we can find a way to bring it down. So, but we can't just move that x down without changing the overall value of the equation. So an easy way to allow the variable exponent to move between exponent and base level is we involve natural log. Log properties allows the exponent to move freely back and forth. So if I take the natural log of both sides, the strategy here is I can take, as long as I do the process on one side of the equation, and I repeat that process on the other side, I can maintain balance. And the nice thing now is now that I'm inside the natural log or log expression, this exponent is free to move because that's one of the useful properties of logs. Exponent can freely move down. So x times natural log of e is equal to natural log of 1. Okay. Another useful property, we know natural log of 1 is 0. And then do you guys remember what's natural log of e equal to? Well, e is 2.7, but anyone know what natural log of e is? 1, yeah. So the reason why it's 1 is because natural log is a shorthand way of saying log base e. So it's really log base e of e. And if the base and the value match, essentially, we're using a function in its inverse, kind of canceling each other out. And so natural log of e just goes to 1. So x is equal to natural log of 1, and natural log of 1 is 0. So x equals 0. Right. 47, we'll just, repeat the same process there. Try to get e to the x by itself. And then just like before, take natural log of both sides, bring the x down, and see if we can solve for x. Okay, so try 47. Okay. Get the same answer, basically 47. 48, there's nothing to divide or move over. It's already as simplified as we can get in terms of things that we can move to the right side. So we just want to go ahead and directly take the natural log of both sides because we know that we got to solve for x. We want to find a way to get that 2x to come down. So log properties allows our exponent to freely move. 49, we can work backwards. We know that natural log of 1 is equal to 0, so we can kind of work backwards and realize, okay, well, what x value will allow this to be 0? Natural log of 1 is equal to 0, so x equals 1. Another way that we can do this is understand that natural log is there's a hidden base. It's base e, right? So natural log ln is a shorthand way of saying log base e of x. Now, if I want to get from log to exponential form, I could just start with the base. E raised to the 0 is equal to x. So I can just kind of rearrange it, turn it into an exponential form. Now we can solve for x because e to the 0 is 1. So we've solved for x equals 1. Okay, 50, I'm going to add and subtract in a way where I can get natural log of x by itself and then see what we can do next. So I'm going to subtract 3 from the right side to the left side. 3 minus 3 is 0. I'll move that minus natural log of x to positive natural log of x. X is going to be equal to 1, but we can also convert it to exponential form to decide what happens. Natural log of x, same thing as log base e of x. When we convert x to exponential form, we start with the base. The base is e. E raised to the 0 is equal to x. That's the way that we can go from log form to exponential form. Okay, 51, natural log of 3x equals to 1. Let me get that base to show up. Natural log is same thing as log base e. So there's another way that you can do this. We can convert to exponential form and say e to the 0 is equal to 3x. And then 1 is equal to 3x. And so therefore x is equal to 1/3. That's one way. Another way is taking advantage of the fact that logs and exponentials are inverses of each other. And we can find a way to get the e's to cancel out. So just like log base e of e is equal to 0 is equal to x, or log base e of e cancels out. Same thing with if I have e raised to the log base of e. So if I stick a log inside an exponential function of base e, they're also going to cancel each other out. So if I raise both sides with e as the base, I can get some things to cancel out nicely. E and log base e will kind of naturally take each other out. And then we're left with 3x is equal to e to the 0, and e to the 0 is equal to 1, and we get the same result. X is 1/3. Okay, next page. Let me review a couple of exponent and log properties at the top of the page. So page 12. If my bases are the same, let's say if it was like 2 to the x is equal to 2 to the 4x plus 1. If the bases match and I have b to the x equals b to the y, I can just drop the bases and just set the exponents equal to each other. Some exponent properties, if I have the sum of two exponents raised to the same base, I can split that up into the product of two separate bases. So if I have if I have 2 to the 2 plus 3, that's the same thing as 2 squared times 2 cubed. Likewise, if I have exponents subtracted, I can split that up into the division or quotient of two bases. Or I can go the other direction. If I have a to the m over n, I can clean that up to be a to the m minus n. But if I have two exponents directly next to each other, that means I can multiply them. So sometimes we get a little bit thrown off by a to the m times a to the n. We think that we can just multiply the exponents here. We're going to be adding the exponents. But if the exponents are directly next to each other, like here, then I can multiply them. We talked about this log property where if I have a log raised to an exponent, that exponent is free to move as coefficient. But there's also two helpful properties. If I have natural log of a times b, I can expand that out into natural log of a plus natural log of b. Or I can go the other direction, depending on whichever way is going to help me move forward with my problem. Likewise, if I have natural log of a over b, I can expand that into natural log of a minus natural log of b. These are equivalent. Sometimes it's easier to move forward with the problem in the condensed form or in the expanded form, but it's just nice to know properties to help us give us some options in terms of solving an equation. Natural log of x is the same thing as log base e of x. Sometimes seeing the base is helpful in deciding our next step. This is kind of a shorthand way of saying that there's a log base e of x. And then some nice order pairs with natural log. Natural log of 1 is equal to 0. Natural log of e is equal to 1. And natural log of 0 does not exist because with natural log of x, there is a vertical asymptote at x equals 0. So natural log of 0 is undefined. Okay, so let's look at 52. 52 is just factoring and solving. There's no exponentials here. Okay, 53, we can factor GCF out. Set both parts equal to 0. Here, e to the x equal to 0. Remember, if I want to solve for an exponent variable, I can always take natural log of both sides. So if I do that, natural log of e to the x equals natural log of 0. Bring the x down. X times natural log of e equals natural log of 0. The issue, the left side is not the issue. X times 1 is fine. It's this, right? Natural log of 0 is what? Undefined, right? So x is undefined, so there's no solution here. The only solution we get is x is negative 1. 54, we can also factor. Our GCF is e to the x. So if I divide out e to the x from e to 2x, I'm still left with e to the x, right? Because I know e to the x times e to the x, I'm going to be adding exponents. E to the x times e to the x, I think is e to the 2x. Set both p equal to 0. Okay, e to the x equals 0. We're going to get the same issue here. No solution. E to the x equals to 1. We can take the natural log of both sides. Bring the x down. Natural log of 1 is 0. Natural log of e is 1. X equals 0. So that is valid. Okay. All right, 55. We're going to solve these log equations. The log base 81 of root 3 equals to x. This is kind of a messy form. So if I can get it into exponential form, I think it's a little bit easier to see where the pieces fit. So we can always convert from log form to exponential form by starting with the base, raising it to the exponent, which is sitting on the other side, and then coming back to the value there. So here, my base is 81, so I can say 81 raised to the x is equal to root 3. Right, it still feels a little messy here. 81 raised to the x equals root 3. But the idea is, well, if I can somehow get the bases to match, then I can just drop the bases and set up, look at the exponent. So I'm looking at the base 3 here, 3 as a common base maybe, and I can maybe get both of these to be something with the base 3. 81 is 3 to what power? You guys know? 3 to the 4th, yeah, because 3 times 3 is 9, 9 times 9 is 81. So 3 to the 4th, and then I can leave that x there. And then root 3 can be written as 3 to what power? 1/2, right? And if I can get the bases to match, then I can take this property here. If b to the x equals b to the y, I can just drop the bases and just focus my attention on setting the exponents equal to each other. So the bases can drop because now they're matching. So now I can say 4x equals to 1/2. Dividing by 4 is the same thing as multiplying by the reciprocal. So I divide by 4, I can think of it as multiplying by 1/4. Okay, part B. This looks messy, but if I can get it into exponential form, then maybe it's a little bit easier to think in terms of exponent rather than this log form. So I'm going to start with my base x, x raised to what power? 1/2, yeah. Is equal to this expression, 64, what is that number? To the 1/3. Okay. Now this, we can actually work it down to a number here. 64 to the 1/3 is the same thing as cube root of 64. Anyone know what the cube root of 64 is? What? Yeah. 3 of the same numbers that can multiply by each other to get to 64 is 4, right? 4 times 4 times 4 is 64. So cube root of 64 is 4. So now I have x to the 1/2 is equal to, yes, question. It's just across the hall, so no, let me just go. All right, so x to the 1/2 is equal to 4, which is really saying square root of x is equal to 4. And if I want to solve for x, I want to undo that square root. So if I want to undo that square root, I'm going to square both sides. So root x squared is just x. 4 squared is 16. Okay, part C. I want to solve for x. X is stuck inside log expression, but first let's see if we can combine some like terms. 9 minus 4 is 5. log form feels a little difficult to work with, but I can always get it into exponential form. So start with a base 2, raised to the 5th power is equal to my expression. I think the general strategy in terms of, when do we go from one form to the other? If my variable is stuck inside a log expression, typically we want to get it into the exponential form to kind of release it from inside that log. It makes it a little easier to work with. And likewise, if the variable that I'm working with is in the exponent of my exponential equation, then I want to involve logs to allow that exponent to come down, and I can work with that variable easier. So we kind of want to, it's nice to have logs and exponentials to allow one to work with the other to get it into the easier form for us to solve the equation. So this is a lot easier to work with, right? 2 to the 5th equals x plus 3. This feels pretty straightforward. I can just get that value, subtract 3, and then I can solve for x. Okay, next one. Natural log of x equals natural log of 8. With this one, I see that, well, they're both showing natural log. So if I can get natural log equals a natural log, then I can essentially drop the natural log on both sides. The issue is that there's a 1/3 sticking here. So I want to get this to a different form. Where else can I put that 1/3 within this 1/3 natural log of x? Exponent, right? I can sometimes we want to bring it down. Sometimes if we put it back up, we can get the proper form that is more helpful to us. So now I have apples to apples here. Natural log of x to the 1/3 equals natural log of 8. I could basically just remove natural log from both sides and then set the remaining expressions equal to each other. So right now, the left side is showing cube root of 8, cube root of x, which is the same thing as x to the 1/3. And if I cube both sides, I can get the 1/3 to disappear, and I can get x by itself. So cube both sides, 1/3 times 3 is 1, and 8 to the 3rd power, leave that alone, or you can write it as 5/12. Take part E, log base b of 8 equals log base b of x plus log base b of x minus 2. I do want to eventually drop all the logs, just like how I did with part D, but I first have to do a little bit of cleanup because I can't drop the logs just yet. I need to do something here. And this is we have a condensing property available. So if I have log of a plus log of b, I can condense it into log of a times b. This property can be applied for log base e, log base 2, log base 3. Any logs of the same base can all we can use these properties for any logs as long as they're within this. They're all showing the same base within the equation. So here I can combine that right side, log base b of x plus log base b of x minus 2 is the same thing as log base b of x times x minus 2. So now I have log base b equals to log base b. I can now drop or take away log base b from both sides, and I can focus on my equation here. 8 is equal to x times x minus 2. Now, can I do this? Can I just say x equals 8 and then x minus 2 equals 8? It feels like that's something that would work, right? But we can only set factored form equal to the other side if this is showing a what? Yeah, 0. If it's any other number, I know it's tempting because it feels like, oh, just so it feels like it's so intuitive, right? Just set everything, set the factor form equal to that number and solve for x, but it doesn't work out. So the only way that's going to work if there's a 0 here. So our next option, because we can't do that, we got to bring everything equal to one side, and then we may have to go through trinomial factoring. Okay, so it's tempting to want to solve for x at this stage, but if it's not showing 0, we got to do something else. So I got to show a 0. Then I have to subtract that 8 over. I know that you would rather want to solve for x at this stage, but we're gonna have to do trinomial factoring. This is not going to give us the correct solution. Okay, so this can factor, right? Multiplies to be -8, adds it to be -2. Solve for x. Okay, now we can solve for x. All right, now that we have factored form on one side and 0 on the other, but at this stage, we're not going to be able to get the right answer. So if you're inside a log equation, there could be some extraneous solutions. So that means I have to go back and plug in my x and see if it's causing any logs to be less than 0 or equal to 0, right? We know that log expressions log value can only exist to the right of 0. Any to the left of 0 is undefined. I can't have natural log of a negative value or log of a negative value. So 4 is fine, but -2 is an issue because -2, if it causes even one of the log terms to be a negative, then I have to remove it as an extraneous solution. Okay, part F. I want to get to x, but x is stuck inside the natural log. But first, let's see if we can do some cleanup. The 4 and 12 can actually divide out. We can move that 4 over. So I want to get to x plus 3, but x plus 3 is stuck inside log expressions. So if I can somehow get it into exponential form, I can get that natural log out of the way. So sometimes I like to rewrite it so I can actually see what base I'm working with. ln is a shorthand way of saying log base e. And now that I have my base showing, let's see if we can get it into exponential form and get that log out of the way. So e to the 3rd power is equal to x plus 3. So now we have a much more we have a lot more flexibility in terms of solving for x. Right now, it feels a lot easier to get x by itself. So e to the 3rd power is going to be some decimal number. So we just subtract 3. So we can just leave it in this form but roughly it's like 2.7 to the 3rd power is maybe like somewhere between in that 20 range. But we can leave it in exact form. Okay, e to the 3x equals 6. I want to solve for x. X is stuck in the exponent. So we want to prefer to have that exponent down at the base level. So if we want to move it, we want to have a log expression to allow for that property to be applied. So I'm going to take the natural log of both sides. That exponent is now free to move because of our log property. Natural log of e goes away. That's just 1. 3x equals natural log of 6. Divide both sides by 3. Okay, part H, I want to solve for x. X is stuck in the exponent. So I'll just involve natural log so that my exponent can be free to move. Let the exponent come down. Let me divide that natural log of 7 over to the right side. It's not gonna, my answer may not look simplified, but as long as I can get x by itself, that's all I care about. I can just add 4 to whatever that number is on the right side. Hey, so remember that I'm going to be checking your entire packet on Monday. So these remaining pages, what I think I'm going to do is I'm just going to highlight a few problems from each part so that you can kind of see an example of a problem, and then hopefully you guys can start working on completing the pages rather than waiting until Sunday to finish everything. So we've gone through most of the packet, but I'm going to see if I can spend rest of this class today and tomorrow just highlighting a few problems, and then hopefully you guys can spend a few days to finish up for Monday. So let's look at page 13, number 1. Let me just do part A and B. Okay, so it says for the piecewise function, find each of the following. I want to find p of -3. So I want to plug -3 either into the first or second expression, but the restriction is going to tell me which one to use. So p of -3, which one will I choose to plug into the first or the second? Is -3, is it less than 5 or is it more than 5? First one, right? -3 is less than 5, so that means there's two separate graphs, right? This graph is existing to the left of 5. This one is existing to the right of 5. We want to find the y value where the graph exists. So it's going to be with that root x plus 4. Okay, p of 0. Which restriction is a better fit? First or second? First one, yeah. So 0 is less than 5, so plug 0 into the x for the first piecewise. So 0 plus 4 is 4, root 4 is 2. Okay, let's look at number 2 here. Simplify the following, given that all angles are between 0 and pi. So this is some kind of problem within the problem here. Arc cosine of root 2 over 2. Let's focus on that piece first. This arc cosine, which is the same thing as inverse cosine, is really representing theta. So this is where theta is. So let's just figure out what that theta is. So theta is arc cosine of root 2 over 2, which is another way of saying cosine of theta is equal to root 2 over 2. And these all mean the same thing. It's just this is written in a way that allows an expression to represent theta. So this feels a lot more manageable, right? Think about our unit circle value. Cosine of what radian measure will give us root 2 over 2? Pi over 4, right? So now I'm going to replace pi over 4 in for that arc cosine of root 2 over 2, and I can further evaluate. So sine of 2 times pi over 4. Okay, what's 2 times pi over 4? Pi over 2. And now this feels a lot more familiar, right? Sine of pi over 2 is equal to 1. Okay, part B, we're going to find each piece separately. Our cosine of 0 is basically saying cosine of what theta value is equal to 0. We're going to figure out that piece. And arcsine of 1/2 is another way of saying sine of what theta value is equal to 1/2. And so if we can find the thetas for both of these, we can put them in place of our cosine, and then we can add them and then do the final cosine. So cosine of what theta value is equal to 0. Yep. And then sine of what theta value is equal to 1/2. Pi over 6, yeah. So now we're going to add these two together, and then we can ultimately find cosine of the resulting sum of my radians. So pi over 2 plus pi over 6, let's do that to the side. I do need common denominators, right? So common denominator is 6, so pi over 2 is the same thing as 3 pi over 6. Which is 4 pi over 6, which is 2 pi over 3. So now we can replace this whole thing with 2 pi over 3, and now we can ask the question, what's cosine of 2 pi over 3? We know cosine of pi over 3 is 1/2, but second quadrant cosine will be what, positive or negative? Negative, right? So -1. Number 3, rewrite each of the following as an algebraic expression with no trig involved. Hint, draw triangles, and use Pythagorean theorem. So let's figure out this piece here. Our cosine of 2x, that's another way of saying cosine of theta is equal to 2x. I'm going to force a fraction out of this. I'll say 2x over 1. Okay. That's basically what that inside parentheses is representing. Cosine theta equals 2x over 1. Now, let's draw a triangle that represents this ratio. So let's create a triangle in the first quadrant here. Cosine of theta equals 2x over 1. Remember SOHCAHTOA. What is the relationship for cosine? Cosine is what? Adjacent over hypotenuse, right? So the 2x is my adjacent side. 1 is my hypotenuse. So I'll say put 2x down here and a 1 up here. What can I do to find that third missing side of my right triangle? If I have two sides of a right triangle, how can I find the third side of a right triangle? Pythagorean theorem, right? A squared plus b squared equals c squared. So I can say 2x quantity squared plus b squared is equal to c squared. I'll let my c squared be my hypotenuse. The b squared is equal to 1 minus 4x squared, which if I take the square root is square root of 1 minus 4x. That makes sense? Any questions there? Can I reduce this to just be 1 minus 2x and drop the square root? What do you guys think? Okay. That minus is getting in the way. I know it's tempting to want to deal with the square root. Now, if I just have square root of 4x squared, then yes, I can break that down into root 4, which is 2, root x squared, which is x. But as soon as there is a addition or subtraction, I'm kind of stuck. I can't just cancel out. The algebra doesn't clean up as nicely as we would like. So now that we have this triangle in front of us, we can turn around and say, okay, I'm ultimately trying to find the sine of theta. Because our cosine 2x is this triangle here. So what's sine of theta now? Sine is what? Opposite over hypotenuse, right? So my opposite from theta is root 1 minus 4x squared. My hypotenuse is 1. So sine of theta is just root 1 minus 4x squared over 1. I can drop the 1 if I want. Okay, why don't you guys try part B and I'll work alongside you guys. Okay, so tomorrow I'm going to see if I can kind of do a few problems from each section to finish off the packet and then have you guys finish the rest over the weekend. Okay, so and then I'll check the packet on. All right, come get your phones.